Okay, we're going to talk about the birthday paradox. And the birthday paradox is all over the internet. Okay, anywhere you go, you Google birthday paradox or birthday probability, and you'll have a Google page full of sites that calculate the birthday paradox. And what I want to do in this video is show you that, or prove to you that, the birthday paradox, as is calculated everywhere on the internet by some good-hearted folks, is not what it reads. Okay, and the birthday paradox says, well, let's get started. Let's talk about it. The birthday paradox, and it has amazed me about how people calculate the birthday paradox. The birthday paradox is this. Suppose you have an event or a room that contains n number of people. At what n number of people is there a probability of 50% that two of those people share the same birthday? Okay. Everywhere on the internet I look, everyone calculates the birthday paradox and get the same answer of 23 people. As a result, this means that if you have at least 23 people in the room, there's a 50% chance at least two people will share the same birthday. That's what they say. It says that everywhere. And everywhere I've looked, it says that. And that's not true. But let's continue on. I calculate this much differently. I also disagree with the widely publicized answer. It is 23, but for the wrong reason. I disagree with it because it is correct for the wrong reason. How many times were you at an event, say on a job with 23 people, and one of them had the same birthday as you? You probably haven't. You probably can't remember because it doesn't happen very much. I was born on June 23rd. I've been an engineer for 32 years at 4 different companies in 4 different states, and I'm still waiting to see it happen. 50% chance in a group of at least 23 random selected people, and someone else in the group was born on June 23rd, but people keep saying it, and I haven't found it. Okay. Well, I'm going to calculate this birthday paradox for you and prove to you why it's correct for the wrong reason by the method that is currently used all over the internet. All or most of these folks doing the calculation start out using the number 23 and don't calculate it, but we will. First, let's define exactly what we intend when we say birthday. There's birthday with the hyphen, meaning the same day, and birthday. Birthday is June 23rd for me, and probably for you it's some other month and day, okay? So birthday means the day you were born. Birthday means the month and day you were born. So if I say there's a 50% probability that in a room of 23 people, a person shares your birthday, I mean the day you were born, not the month and day you were born. Well, we're going to show that. So let's get started. Matching birthday. We're going to take their problem first, okay? And let's say a room is filled with n people, n number of randomly selected people. What's the probability that at least 2 people in that room share the same birthday? How many people would it have to be in this room for you to have a 50% chance of finding at least 2 people with the same birthday? Okay, with the hyphen. Remember, we're still with the hyphen now. Okay, so this is the problem. We have a group of n people gathered together. What is the value of n if the probability is 50% that at least 2 people in the room share the same birthday? This is the problem we're going to solve. So let's get started. Okay, I know at a pro football game of 70,000 people, someone shares the same birthday. But let's say this is a company meeting or a party. How many people would have to be in attendance to assure 50% chance that two people share a birthday? Let's calculate this. Okay. The problem. There are 365 days in a year. Dismiss leap years and extra days in the month occurrences like February 29th. We can calculate that one too. But let's stay with the internet problem. Okay. How many people should be present in this gathering? Okay, what's probability? Probability equals the number of ways that an event can happen divided by the total number of ways that any possible outcome could happen. So, since there are 365 days in a calendar year, which each person we say should and can only be born on one of those days, what's the probability that one person in the room was born on one of those days? What's the probability that no person in the room was born on one of those days? Well, the probability of picking the correct day is 1 over 365. And the probability of not picking the correct day is 1 minus 1 over 365. Okay, that comes out to be 364 divided by 365. I say 1 over 365 because it's the probability of selecting the day correctly. Then I have one success. And if I have one success, then selecting any of the other 364 days must be a failure. Okay? Let's continue. So, let's see what happens if I calculate the probability of no two people sharing the same birthday. Let's investigate this. Since each person's birthday are independent events, then I just multiply the probabilities. But how many times do I multiply? Well, I need to know how many combination of days of the year I will have. But this depends on how many people are in the specific room or in this specific room, which I still don't know. So let's write out an equation for this. By the way, I'm not using 23, so at this point, I don't know what the number of people should be. The probability, let's let P equal probability. Then the probability of success equals 1 minus the probability of failure. And we already know what our probability of failure is. We just said it was 364 over 365. So the probability of success equals 1 minus 364 divided by 365. Right here, 364 divided by 365. But now we said we have to multiply that by some number. And I'll call that number C of n choose 2, or n given 2. Or n choose 2. And you'll see what that means later. Okay? And C of the n choose 2 is a combination. N people taking 2 at a time. Okay? So the probability of success equals 1 minus 364 divided by 365 raised to the power of this factor here we have, which we haven't calculated yet. When we also say the probability of success or failure is 50%. Okay? So, we'll put in 50% for probability of success. And that equals to, 50% is equal to 1 minus our factor here, our equation, 364 divided by 365, raised to some power of a combination. And we solved that, changed 50% to a decimal. And that gives us 1 minus 364 divided by 365 raised to some power of that factor is equal to 0.5. I just rearranged the equation. And then I bring the 0.5 to the other side, and I subtract it. 0.5 from 1 is 0.5. So that leaves us with 364 divided by 365 raised to some power, okay, equals 0.5. Now we need some 10th grade and 11th grade mathematics, which we call logarithms. I guess when you were in high school, you was wondering, what will I ever do with logarithms? Well, here it is. Take the natural log of both sides to solve for the exponent. And this is not a logarithm video, so if you don't know how to use logarithms, you need to look up a logarithm video. I haven't done a video on logarithms yet. But we have our equation here equal to 0.5. And when we take the log of both sides, the log of this left side and the log of the right side, and then we take the power due to the properties of logarithms, okay, and we divide through by log of 364 by 365, and that's, we plug it into our calculator with minus 0.693147 divided by minus 0.002743, and we do that division, we come up with 252.65. We round that off to 253. So now we see that our C to the n choose 2 is 253. Okay. But that still doesn't tell us what our n value is. So our pairings have to result in 253 combinations, rounded off. But we will still need to know the value for n. N is the number of people in the room. Okay, so let's do that. As I said before, 253 is combinations. C, the combination n choose 2 is n people taking 2 at a time. But this is a factorial. Okay, so let's do that. N choose 2. N choose 2 is written the n factorial divided by 2 factorial times the quantity n minus 2. Okay? N factorial is equal to n times n minus 1 times n minus 2 factorial. Okay? So therefore, replacing n factorial with what we said it is here, and we get n times n minus 1 factorial times n times n minus 1 times n minus 2 factorial divided by 2 factorial times n minus 2 factorial. Well, these n minus 2 factorials cancel. 2 factorials is 2 times 1, so that leaves us with n times n times quantity n minus 1 divided by 2 equals 253, because we said it up here as 253. Okay, so now we can solve for n. Okay, and we multiply through by n, that's n squared minus n over 2 is equal to 253. N squared minus n equals 506. So n squared minus n minus 506 equals 0. Okay, and this is just a 9th grade quadratic equation. And you were wondering what you would ever use quadratic equations for. Well, here it is. Okay. The formula for the quadratic equation is n equals minus b plus or minus the square root of b squared minus 4 times a times c divided by 2a. Okay? So, n squared minus n minus 506 equals 0. And in our equation, a is equal to 1, the coefficient of n squared. B is equal to minus 1, the coefficient of n. And c is equal to minus 506. Which is our constant. So we just plug those into the equation here, the quadratic equation. And we plug them in, and as we plug them in, we multiply through by these negatives. Negative times negative is a positive, so we get that plus 1, plus or minus the square root of 1 plus 20, 24, equals 1 plus or minus the square root of 20, 25 divided by 2. Okay? And we carry out that multiplication and division, and we get plus or minus 23. And we know it's not minus because we don't have minus people. So we have n equals plus 23, since we don't have any negative people. You can go back and check your answer on C. 23 given 2. We'll substitute 23 for n, and you'll get 23 factorial divided by 2 factorial divided by 23 minus 2 factorial, and to do that you'll get 253 as before. Now, if you're doing this on a calculator, I believe the calculator, highest it goes on factorials is 50. So you won't be able to do any numbers past 50, but 23 it'll do it just fine. Therefore, back to our original equation. The probability of success equals 1 minus 364 divided by 365 raised to some power. Well, we know what that power is now. It's 253. Okay, so we raise 364 divided by 365 to a power of 253, and we get 1 minus 0.49952. And we subtract that, and we get 50.04%. So the probability of success is 50.04%. Therefore, if there are at least 23 people in a room, there's a probability of 50% that at least 2 people will share the same birthday. That means the same day of birth. That doesn't mean birthday. Okay. Same day of birth. Let's graph this and see how it looks. Now, the folks that used 23, they just started out with 23, and they just took 365 and they went down to 23 numbers, and they came up with 343. Okay, and then they divided by 365, and they come up with a 50.07 answer, I think it is. But they did that for 23 people. Okay. Here it is. Okay. So here's our probabilities on the vertical axis, and here's the number of birthdays on the horizontal axis. And we have 1, 2, 3. And we go up to 50%, and there it is. At 50%, at 23 people in the room, we got a 50-50 chance that 2 people in this room will share the same birthday. Okay? At 23 people. For an example, for 45 randomly selected birthdays, 45, right there, is just above 92%. We've had 44 presidents, and 2 share the same birthday, James Polk and Warren Harding. They were both born on November 2nd. It just so happens that they were born in the same month. But this calculation doesn't calculate that. It just calculates the same day. We just got lucky with the same month also. Okay. Now let's do the birthday problem without the hyphen. Okay. So since there are 365 calendar year, 365 days in a calendar year and 12 months in a year, which each person we say should and can be born on one of these days and in one of these months, what's the probability that one person in the room was born on one of these days, as before? What's the probability that no person was born on one of these days, as before? Okay, we did that before. But now here's the catch. What's the probability that one person in the room was born in one of these 12 months? Okay. What's the probability that no person in the room was born on one of these 12 months? We have to answer these questions. Okay, let's answer these questions. The probability of picking the correct day, as we saw as before, is 1 over 365. The probability of not picking the correct day, as we saw before, was 364 divided by 365. But now we have, what's the probability of picking the correct month? Well, the correct month, picking the correct month is 1 over 12, 1 divided by 12. And what's the probability of not picking the correct month? Well, that's 11 divided by 12. Okay. I say 1 over 365 because it's the probability of selecting the correct day, the day correctly. Then I have one success. If I have one success, then selecting any of the other 364 days must be failures. Okay? I say 1 over 12 because it's the probability of selecting the month correctly. Then I have one success. And if I have one success, then selecting any of the other 12 months must be failures. Okay? If my birthday is on June 23rd, then there are 12 more months that contain the 23rd. Okay? There's January 23rd, there's February 23rd, March 23rd, all the way up to December 23rd. So if I'm picking the correct day of the 23rd, I have 12 more months I can pick from, okay? So not only do I have to select the correct day from a field of 365 days, as with birthday, I must also select the correct month from a field of 12 months. Okay? Therefore, my probability of success in the total selection is 1 over 365 times 1 over 12. Okay? Since each person's birthday are independent events, then I just multiply the probabilities for each n persons. But how many times do I multiply? Well, I need to know how many combination of days of the year and months of the year I will have. But this depends on how many people are in this specific room, which I still don't know. So let's write out the equation. Probability equals probability of success. P equals probability. And the probability of success, as before, was 1 minus the probability of failure. So the probability of success is 1 over 12 divided by the probability of success is 1 divided by 12 times 365, which is 4380. Okay. So the probability of failure is just 1 minus 1 over 4380, which is 4379. Okay. Last time, what we did was the probability of success was 1 over 365. And we said the probability of failure was 1 minus 1 over 365, which was 364 divided by 365. Okay, but now our probability of success is 1 divided by 12 times 365, which is 1 over 4380. Okay, and so when we subtract that from 1, we get the probability of failure, 4379 divided by 4380. And so now our probability of success is equal to 1 minus the quantity 4379 divided by 4380 raised to some power. And that power is what we have to calculate. Okay. Now, see the combination n choose 2 is the total times I must multiply. Okay? So that's my quantity here. Right there. Cn choose 2. Okay. So the probability of success is equal to 1 minus the quantity 4379 divided by 4380 raised to the power of this quantity. Okay. So let's calculate that quantity. Well, we said the probability of success was 50%. Okay. So we do as before. We put in our 50%, change it to a decimal right here, and then we change the equation over as we did before, move 0.5 over to the left side and our quantity over to the right side, and we end up with that. And so we have our quantity raised to a power equals 0.5, and we got to take logarithms as before. Okay, we take the natural log of both sides as before, and we come up with the same equation again, but now we're dividing by a different quantity, okay? So we have our probability, combination n choose 2 is equal to the log of 0.5 divided by the log of the quantity, 4379, divided by 4380, okay? And we do that calculation, we do that computer input, and we get this number. C to the n choose 2 is equal to 3035.63, and round that off to 3036 combinations. So C to the n is the multiplier, and so our pairings will result in 3036 combinations, rounded off. But we still need to know what n is. Well, we did that before. So n is the number of people in the room, okay? So, as before, our combination is equal to 3036 combinations, 3036 combinations, and C n choose 2 is n people taking 2 at a time, okay? And C the n choose 2 is a factorial, okay? It can be written as this. So n factorial divided by 2 factorial divided by the quantity n minus 2 factorial, as we did before, okay? And so we come up with the same thing as we did before. The n minus 2 factorials cancel out. And we solve for n times n minus 1 divided by 2 equals 3036. And we plug that in and do our multiplications and our divisions. And we come up with our quadratic equation. Okay, as we did before. But now we got a different number. So let's solve this quadratic equation as we did previously, okay? The formula for the quadratic equation is as it was before. It's been the same, it hasn't changed. N squared, the coefficient A equals 1 is for the coefficient of n squared. B equals minus 1 is the coefficient of n. And our constant is minus 6072, okay? So we plug those, do our multiplications of our negative numbers, and we come up with 1 plus or minus the square root of 1 plus 24,288. Okay, we add 1 to that, 24,289. Okay, divided by 2. And we take the square root and perform all those calculations. And we come up with plus or minus 78.4. Well, we round that off to 78. Since we can't do 0.4 people, okay? Since we don't have negative numbers, then we take the plus, n plus 78, okay? Therefore, our probability of success is equal to 1 minus 4379 divided by 4380 raised to this power, and we know what that power is now, 3036. So we raise that to the power of 3036, where we do our division, then we raise it to a power of 3036, and we get our probability of success is 1 minus 0.499958, which is equal to 50%, as we said. So therefore, if there is at least 78 randomly selected people in a room, there's a probability of 50% that at least 2 people will share the same birthday. That means month and day. So you got to have at least 78 people to have a 50-50 chance that 2 people share the same month and day birthday. Let's graph this. Okay, so we go out to 78 people, okay, with 73 is here, and we go out to 78 people, and voila, 78 people at 50%, okay. For 45 randomly selected birthdays, the probability of the same birthday, of sharing the same birthday, day and month, is 20%, right here. For 45 birthdays, it's 20% chance. We have 44 presidents, and 2 share the same birthday. James Polk and Warren Harding were both born on November 2nd. They were born in the same month and on the same day. That's 20% chance at 45 randomly selected people. If you want a 50% chance, you would have to have 78 people. Okay? But at 45 selected people, it was 20%. And we got lucky. Okay. So what is the solution to our problem? 78 people. With at least 78 randomly selected people in the room, there's a 50% probability that 2 people in the room will share a birthday. Same day and same month. Now, if you're looking for just the same day, all you need is 23 people in the room for a 50% probability. With at least 23 randomly selected people in the room, there's a 50% probability that 2 people in the room will share a birthday, same day of birth. Okay. Here's a note. At this moment, there are 318,351,131 people in the United States at this moment. I got that from the population clock, which I've included in this video. Okay. I believe there's a birth every 8 seconds. I think you look at the population clock and see. But it's quite different than it is. It's quite different now than it was when I made this video. Okay. The probability of success is equal to 1 over 43. The probability of success for birthdays is 1 divided by 4380. And this is the U.S. population I just quoted. People that share your birthday, day and month, 1 over 4380 times the population is equal to 72,683 people born on the same month and day as you. Okay? The probability of success picking the correct day is 1 over 365. Multiply that by the population. The people that share your birth hyphen day is 1 over 365 multiplied by the population. And that's equal to 872,194 people born on the same day as you. Okay? The probability of success is 1 over 12 for picking the correct month. Multiply that by the population. The people that share your birth month in the United States is 26,529,261 people born in the same month as you. And these are the correct numbers. Okay? So there's 72,683 people that share your same month and day in the United States. And finally, how common is your birthday? Here's a link I found on the internet. And here's a good laugh. The Tonight Show with Johnny Carson, Birthday Paradox. The first video he got it wrong. The second video he got it right, but he was still wrong. Okay? And then the first one was on February 7th, 1980. You can watch this video if it's still out there. You know, we click here. And if you want to watch how he got it, he corrected it. It's February 8th, 1980. Okay? And I enjoy it. Every time I look at it, I enjoy it. And here is a link to the U.S. and world population clock. So if you want to do these calculations, you can get the correct population. Okay? I hope you learned something. Math is fun. Until next time. And if you want to discuss this, come to my Facebook page. I hope you learned something.